You think physics is what physics is, but classical computers are built on electronics and a physics that we understand in terms of the flow of electrons. Quantum computers are built on quantum physics, and in particular, there are two properties of quantum physics that we used. One of those is superposition, and the other property we call entanglement.
Hello and welcome to this episode of the Digital Humans podcast. I'm Paul Ashcroft. This podcast explores what it means to be human in a world where technology is rapidly reshaping our reality. We meet entrepreneurs, startups, and industry pioneers at the forefront of innovation, diving into breakthrough ideas and disruptive technologies that are shaping our future. Today's episode is all about quantum computing, and we're delighted to be joined by our guest today, Nathan Phillips from TreQ. Nathan has over 20 years' experience managing the development of advanced commercial software products for large corporate and public sector clients in a variety of industries. He holds a degree in computation from the University of Oxford, and with this experience, he's now bringing best practice methodologies, architectures, and patterns to the world of quantum-enabling classical software. His passions centre around compilers, domain-specific languages, and the hardware-software interface. We're delighted to have you with us today, Nathan. Welcome to the podcast.
Thank you, Paul. I'm excited to be here. It's very timely.
There's a lot there even in your bio as I read it out for us to unpack. But first, I've got to say, for those that are watching the video, I have complete background envy today. Nathan is sitting there with a bona fide quantum computer behind him, aren't you, Nathan?
Not currently operating, and anyone who knows about it will see there's some key bits not connected at the moment. But yeah, you're right. This is all the key components of a quantum computer.
Well, why don't we start there? Why don't you please just tell us a bit about yourself and about TreQ?
As I said, it seems like a really timely interview. This is actually just most of my team aren't here today because they're all off in America preparing for next week's Global Physics Summit hosted by the American Physical Society. It's International Year of Quantum Science and Technology, so quantum computing is taking center stage there. So we've got all hands on deck over in America. Exciting times. TreQ is a startup. We raised $5 million last year on the back of a premise that the world of quantum computing is reaching an inflection point. And by that, I mean, it's moving out of academic laboratory sort of spaces and into the manufacturing space, from toys for doing experiments with heading towards appliances for commercial application. And so we're building a business where we're taking manufacturing techniques to actually manufacture quantum computers built on an open architecture. By open architecture, I mean where different supply chains come together with fixed interfaces between them. And so having this interoperable model where we can combine the best technology from a variety of suppliers into useful machines. As for me personally, I'm pretty new to this world. I only officially joined TreQ last November. One of TreQ's principles is that the quantum industry has a lot to learn from the surrounding industries on which it's built. So I bring kind of best practice from the world of software development, those methodologies and things, to support developing commercial grade software infrastructure around the clever hardware stuff that the physics geeks are doing. It's all part of our vision to move the whole quantum computing experience out of academia and make it something that fits more naturally in the commercial business world that people like you and I are used to spending our time in.
So would you say that TreQ is in that race to build essentially a practical quantum computer, something that is, whether it's affordable, but certainly something that corporations, governments can actually start to use at a more practical level in the way they want to do so? Is that the goal?
There's still a reasonable amount of work to be done towards that goal. And a lot of that work still is going to happen in those laboratories that I've mentioned. I think what we're trying to do is perhaps democratize things, make quantum computers more accessible so that they're not limited to people who have got a team of PhD students on their staff. And actually you can almost order an off-the-shelf quantum computer where something will be delivered and installed for you, and you can be given enough training to get yourself to the point where you can start to experiment with it. Now, who knows quite how long it's going to be before we get to a system where you plug it in and you sit it on your desktop, and that's some way off, as you can see by the size of the thing behind me. But yeah, we're certainly hoping to, let's say, democratize quantum computing.
Let's back up a bit. Maybe dive in first and just tell me and our listeners what exactly is a quantum computer and how is that different from what we would have on our desk today, or which essentially is a classical computer. What are the main differences?
I guess the main difference is that they're built on entirely different sets of physics. You think physics is what physics is, but classical computers are built on electronics and a physics that we understand in terms of the flow of electrons, whereas quantum computers are built on quantum physics. And in particular, there are two properties of quantum physics that we use to enable a whole new different way of doing computing. One of those is, we call it superposition, which enables to literally put an element into a combination of two opposite states at the same time. If we don't know which state it is, it's literally in a combination of those states. And that's superposition. And the other property we call entanglement. That enables us to link the state of one particle to the state of another, even when we can't look at the state of either of them. And that combination of those two properties means we can bring a whole class of problems that classically would be too difficult to solve in a reasonable amount of time. These are intractable problems, or part of the class of NP problems. It brings those problems into the domain of problems that actually are solvable.
What would be an intractable problem? What's an example?
The classical one that you always learn at university is the traveling salesman problem. I don't know how many people need to solve a traveling salesman problem in real life, but problems where you're trying to optimize a complex grid. And these are problems where you can solve it for a salesman traveling between 2 cities. You can solve it for a salesman traveling between 5 cities. With a computer, you can do it for 10 cities. But as you add more stops that they have to go to, the problem doesn't scale linearly. It scales exponentially, or possibly sometimes even worse than exponentially. And that means that those problems, for some size of problem, just become intractable to the point where you can't solve them with classical computing. Classical computing isn't just faster computing. It doesn't just half the time. It changes the scale of the problem. It takes it from an exponentially difficult problem to a linearly difficult problem, let's say. That may not be true in many actual real cases, but that's the principle of what we're trying to achieve.
You focus on a specific area, as I understand. You're focusing on superconducting quantum computers. Why this approach over other approaches, and what are the other approaches that you could have adopted?
TreQ is actually pretty agnostic when it comes to the underlying technology used by the quantum processing units in the machines that we ship. And so that's the thing that is superconducting or trapped ion. And if the technology works and there's demand for it, then TreQ will create a machine using it. And that's part of what I was talking about in the introduction. Until recently, every computer has been built almost as a one-off lab project, with companies trying to own the whole supply chain and do everything in-house. Whereas companies like TreQ, we're bringing the assembly of these things, but not having spent billions of pounds on investing in superconducting quantum processors or trapped ion QPUs. So if somebody says, I want a trapped ion one, we will find the supply chain and do what work needs to be done to make that supply chain work with the machines that we're delivering. But to answer your question directly, you're right. The system we're working on right now, the one behind me, that is a superconducting QPU system. And that's mainly because it's the most established technology. It's the same technologies that Google and IBM are using, for example. And our team has deployed several of this type of system in previous roles. So we have quite a lot of expertise with superconducting. But we're really keen to serve customers that want to include more than one modality in the same quantum cluster. In fact, that's probably one of our chief distinctives as TreQ. We've built our stack around this idea that actually a single quantum cluster could include multiple modalities. You could have a superconducting and a trapped ion system in the same cluster. And that's something I don't think anyone else is doing.
So at the moment, quantum is not in the world of VHS versus Betamax. And one will win? Is one modality likely to win?
It's a really interesting question. And I think we can't answer that yet. It is possible that, so one of the reasons for wanting multimodality clusters at the moment is because we're still trying to compete these things against each other. But even in the long term, I could see a situation in which we will find that certain modalities, certain technologies for QPUs will work better on certain problems. And so you might end up where you do have a system that has more than one type of QPU in it in order to be able to solve more than one type of problem.
Now, one thing I am aware of, maybe our listeners are aware of, is that one particularly special thing about quantum computers, at least today, is they have to operate at incredibly low temperatures, colder than space. Maybe you could tell us, and you talked a bit about the supply chain. So why do they have to operate at such low temperatures? And then how do you get these things to do that? They have a very complicated looking, quite amazing looking structure that is almost unrecognizable as a computer. Why is that? And how do you achieve it?
So those cold temperatures that you've heard about. And you're right, it is colder than space in my office. And that's not just because nobody's turned the aircon on today. The really cold temperatures you heard about are there specifically for semiconductor-based QPUs, which would include the superconducting ones. And there's two reasons for that. Firstly, at the moment, there just aren't any viable options for materials that we could use to fabricate superconducting chips at higher temperatures or pressures than we're working with right now. And secondly, the big problem that we have with interacting with these tiny circuits, these are kind of atom-sized circuits. This problem we have for interacting with is noise. Noise is always our problem. So just the noise of the heat emitted by all the atoms moving around you, we need to get rid of that. And so we're cooling things down to temperature where even air molecules stop moving. So the whole thing operates in a vacuum, and the air molecules tend to end up all stuck to inside of the vacuum shielding. So the actual space inside is a total vacuum. So we're reducing noise. We're creating conditions where our superconductors work. And you're right, it is colder than space. Just the background radiation in space means that however far you are from a star, you're still around 4 Kelvin. And we're operating at less than 50 thousandths of a Kelvin, down to 10 thousandths of a Kelvin. Not quite the coldest place on Earth, but colder than anywhere that's not on Earth. And then I'm on Milton Park, just a couple of miles down the road. We've got a fusion reactor, which is about 500 times hotter than the hottest star in the universe. Humans are amazing, aren't they? Are we not amazing that within 3 miles, we've got the hottest and the coldest places in the universe?
Hopefully don't bring those two things too close together. I'd be afraid of what
Well, the
of
good
what
news
happens.
is we're both operating at, well, the area that we're cooling down is about that size, and the area they're heating up is even smaller. They're heating up very, very small bits. So high temperatures, less heat.
At the heart of a quantum computer then, is it essentially a series of fridges, to put it very plainly, that is sort of allowing you to cool down and cool down and cool down to that level?
Yeah, so in the background behind me is a fridge from a supplier called Maybell. We're based just south of Oxford. There's another great supplier around here called Oxford Instruments. They do fridges as well. And these fridges, they're working on the same principle as the fridge in your house. We use slightly different coolant. So we're using a gas called helium-3. And obviously, as you know, fridges work by taking gases and compressing them and expanding them. And it's the same principle here. So we have at the top of the fridge behind me, that would be room temperature, and then it would drop down by a couple of 100 degrees C, and then drop again by another 50 degrees C, and so eventually end up kind of 4 degrees above absolute zero, and then a couple more stages, we can get that down to the sort of thousandths of a Kelvin above absolute zero. We can, in theory, get more than one QPU in the same fridge. So rather than being a series of fridges, it's more likely that there'll be one fridge with multiple QPUs inside it.
As the technology progresses, and as you say, maybe one day we'll have one of these on our desk, it's going to be the same approach to this. Are we going to have a supercooling device on our desk that's operating our quantum computer? Do you imagine?
You're asking me to predict the future. I'm going to guess no. Yeah, I don't think there's going to be a cryogenic fridge that's any time soon, I'm afraid, Paul.
Yeah, that's a shame.
Yeah, you wanted to make some ice cream.
Okay, let's talk about what we can do with these things. As I understand it, quantum computers are at the moment mainly used, as you said earlier, in an experimentation way. They're in research labs rather than large-scale practical applications. So what needs to happen before they become commercially useful? Why don't we start there?
You're right. We're not there yet in terms of systems that can actually solve commercial problems. The number one thing that we really are looking to solve at the moment is improving performance by solving the problem of errors in the logical gates that we create, the quantum logical gates, and that's through error correction or error mitigation. And there's some big companies dedicating a lot of resources to that problem. Google have made some interesting discoveries recently. There's been quite a lot of encouraging signs on that. There's another major problem, which is scalability. So that's both in terms of making bigger chips with more qubits per QPU, but also in terms of just making more chips more consistently, more reliable chips in batches. And those are problems that we're likely to have to keep chipping away at over many years. That's not something that's going to suddenly be solved with one sudden discovery. And those two things in some ways work together. The more errors that we have, the more qubits we need to implement our logical gates, because we use extra qubits to compensate for that. And so for some real world business cases, I think we're going to need tens of millions of qubits. And at the moment, a large QPU's only got about 1,000. So scalability, we're definitely some way off actual usable systems.
Are there companies using it today? What sort of applications are they currently at least experimenting with?
the world of quantum computing has opened up a lot of opportunities. There are a couple of ways that companies are preparing for quantum readiness, even though we're not there yet. One of those is they're developing IP ready for when the computers are there to enable them to run those things. And so they are investing in quantum computers in order to develop algorithms or applications. Even though the machines needed to fully run those applications are not yet available, they're using these quantum machines to prove the viability of those algorithms. So they've developed the IP and own that IP that mean they'll be at the front of the line for exploiting those machines when they do become available. There are other companies that maybe don't have the resources to throw at a team that can start developing those algorithms, but they still want to be up to date on what's going on. And so they're investing in quantum computers or access to quantum computers in order just to make sure they're training their staff to be aware what quantum computers are, how to use them, and what sort of applications might be useful to them. And as a side benefit, those companies that are investing in developing that IP they are getting some return on investment now because they're developing quantum inspired algorithms. So these are ways of solving problems that can run on the classical hardware we have today. But by thinking about a problem in the way that you would need to in order to solve it on a quantum device, they're coming up with more efficient solutions that can run on classical computers. It's not as good as true quantum computing, but it's a way that people are getting some ROI now, even while we're in the intermediate stages of the development of quantum computing.
Right. Okay. So much like with artificial intelligence, we're learning through application of it how to use this in a better way.
Yeah.
What would you say are some of the impacts that you're seeing on, some perhaps of the known use cases around, say, drug discovery, where there's lots of very complex data sets to go through, finance, cryptography, and so on. What are you seeing how quantum is going to impact some of those industries?
Yeah, I was in a meeting with some representatives from the FCA last week, and they want to be ahead of the curve. They don't want to be a blocker, so that when things do become available, suddenly we start thinking about regulation, how it impacts on those sort of things. So they're already trying to work out now how they're going to work with quantum algorithms when those are available to be run on real computers. But you asked first about drug discovery. Yeah. And on that one, if you want to model a molecule, which is what you're doing in drug discovery, then you are trying to simulate an inherently quantum system. Molecules are quantum systems. And so doing that on a classical computer, it's an exponential problem. It's a problem where as soon as you made anything non-trivial, it takes a very long time. So quantum computer is going to make a massive difference to drug discovery if it can do that sort of thing. Finance is a different market. They're often just trying to throw computing power at the moment to optimization problems. So that's where they'll see benefit from quantum computers, is they're thinking about things like portfolio optimization, but we're just investigating use cases, and there's no definite kind of this is how it's going to definitely improve things. We are still in that early days discovery time. Quantum in AI, I think you mentioned, that is interesting. That's very much an area of hot exploration at the moment. We know some possible quantum applications that would help with machine learning or neural networks, but we expect to see a lot of growth in that application area because obviously there's a lot of people putting money into that at the moment.
The one I do want to click into is encryption technology. The sort of scare story that I hear is that when we do start to have accessibility to quantum computing, then all of the current encryption models are essentially worthless. A quantum computer could work through the best encryption we have at the moment in a matter of seconds, and therefore your banking, your personal data, the encryption that's used behind the military between transport is basically defunct. Is that true, or to what extent is that true? And should we be worried about it now?
Well, don't panic yet, because the QPUs we have at the moment are still too small to crack the RSA that we're using every day. But governments are taking this seriously. So they're investing in quantum ready encryption. And there are a few quantum resistance algorithms already become available. If you are transmitting information that you want to be secure in 10 years time or 20 years time, then you should be using those algorithms now. So you can find those through the US government's website. They did a call quite a while ago now, where they've actually come up with some algorithms that work in a different way that won't be susceptible, or we hope so far won't be susceptible to quantum cracking. But in terms of RSA and the There's some things that we use currently for our banking. Yes, I mean, that's not going to survive proper quantum readiness. And so we will need to change things on the way we do that by then. In some ways, that's probably not the scariest area, though. Some people are saying that the underlying encryption behind Bitcoin won't survive quantum readiness. That's going to cause some disruption, I think. But the thing to be aware of is just what's the lifetime of your data. So if you're doing a bit banking online, does it matter if somebody gets hold of it and in 10 years' time they can read what you did today? What we hear, and I don't know if it's true, but it would be strange in some ways if it wasn't, is that governments, again, I've heard possibly the Chinese, although I don't offend anyone, and probably I'm sure others are doing this as well without us knowing, they're scraping encrypted information being passed over the internet now. Even though they can't read it, they're storing it because they believe that they will be able to read it once quantum computers have scaled up. And so they're targeting anything they think will still be useful intelligence in a 10-year timescale, which tells you something about when they expect to have that sort of technology available.
It's one of those big unknowns, isn't it? How a bit like the artificial intelligence world, it seems to be changing on a weekly basis, this technology, and being prepared for that. I don't know how you prepare for it. It's a wicked problem in and of itself, I suppose. Would you hazard a guess as a time frame as to when quantum is going to start to become more mainstream? Are there some specific milestones that you're seeing or that you see that we will need to have got through in order to get there?
As to how long it's going to be, I will tell you what other people are working on. I guess that's the best I can do. But I mean, we don't need to panic. So it wasn't that long ago that we upgraded all of the encryption on the internet from I think TLS1 to TLS2. And it takes 2 to 3 years to do that, just because of the length of the time that certificates are valid for on the web. We could do the same again. It will be a bigger change. It won't just be a step change. It will be a completely different way of doing things, but it is possible. We can upgrade the web in 2 to 3 years, and it is going to be more than 2 to 3 years before quantum computing causes problems in that sort of way. So, like I said, you've got probably at least 10 years, given sort of timescales that some people are talking about. Others say 20 years. Some people have the difference and say 15 years, but I wouldn't like to say a number.
Is it, if I want to get started today, if I want my own quantum computing, Nathan, can I rent one? I wanted to ask you that. Can I rent space in a quantum computer?
So you've got various levels. You could simulate quantum computers. As long as you only want to do 1 or 2 qubits or maybe a handful of qubits, you could actually simulate a quantum computer on a classical computer. Like I said, it's an exponentially hard problem, but actually it is a problem that can be simulated on a small scale on a classical computer. So if you wanted just to do something very basic and just see what it would look like, you can simulate it, and you can get those simulators online. If you want to use a real quantum computer without any upfront investment, then a lot of the big cloud services, so AWS do a service called Bracket, and Microsoft Azure have got quantum computing available as well. People are struggling with those, partly because of the amount of downtime that those systems are having, but it is an affordable way of getting yourself in without upfront investment. And then beyond that, you are either looking at partnering with a university or leasing. There are some places where you can lease them, or buying one. And if you're buying them, you can spend anything between 12 million and 120 million, depending on where you get it from.
How long does it take to build your own quantum computer? From, I give you an order tomorrow. When could I expect it to be delivered and ready and working for me?
As I said, our team has got quite a lot of experience in building quantum computers. And so we're looking for our first couple of machines, I should probably check this with somebody before promising you a quantum computer in 6 months. But let's say that for you, Paul, I'll do your quantum computer in 6 months.
Fantastic. As long as I've got 120 million.
And I think if you were to ask me again in 2 years, I'd hope that would be down to 3 months. Now, that's partly just down to supply chain. So, like I said, in the past, these things tend to be built as one-off things, whereas we're talking more about a manufacturing way where you keep stock of various components. So there's lead times on a lot of these components that are in the many months sort of area. So if you're starting from nothing and you want to build one, it's going to take you, I would guess, 9 to 18 months. But if you're ordering from someone like TreQ, then you'd be hoping that we're not starting from nothing, but that we already have
components and process. We're getting close to our time. A few closing questions for you. What's one question about your industry you wish people asked more often?
I think that the biggest conception about quantum computers is that they're just extraordinarily powerful, extraordinarily fast computers, whereas in reality, they're useful because they solve one or several small specific classes of problems that are just intractable with classical computers. So the intelligent question I wish people would ask, or people could ask, would be, what sorts of problems do quantum computers solve? Rather than just assuming it's the same things we currently use computers for. And I think you've actually done quite well with your questions. You've captured that pretty well. But quantum computers are never going to run Microsoft Word for you. It's just different sorts of computing.
And it sounds like my takeaway is that they're not going to just replace, at least not in the short term, a traditional computer. They'll work alongside, if anything, or for specialist tasks.
Think of them, do you know what a GPU is? A graphical processing unit. These are things we've had them for a long time. We built them to accelerate 3D graphics on our computers. The main thing they're used for now is AI. So NVIDIA are the big makers of GPUs. Think of a quantum computer, not as a quantum computer, but as a quantum accelerator, like a graphical accelerator. They don't replace a CPU. They work alongside a CPU. So your CPU and your QPU will together solve a problem. And some of the problem will be offloaded onto the GPU, some of the problem will be offloaded onto the QPU, but it's the old traditional CPU that will orchestrate those things together and actually be your interface into that world. And that's why I've got a job, because I come from classical computing background, the non-quantum computing background. I couldn't write a quantum algorithm if you gave me, well, if you gave me a week, it would be good. But if you gave me the rest of the day, I probably couldn't. But I come from a classical computing background. I write the sort of software that we've been writing for years now. And in that world, we're still going to need that. We're still going to need that in order to manage these machines. They're still physical machines. There's magic in the bottom, but the rest of it is all the sort of physics where you can punch it with your hand and it still hurts. It's in one state, and it's got a control hardware around it that needs a classical software to drive it.
Yeah, and I love your journey into this. As you said when we first met, that you wouldn't describe yourself as a quantum physicist originally. You as you say, your path has been into this through your own expertise. It's clearly an exciting and going to be growing industry. What advice would you give to someone who wanted to work in quantum computing? You know, what should they be studying? How do they get into it? What's your advice?
That is an interesting question. I mean, to be honest, at the moment, the industry is small. It does feel like there aren't many people in it who don't have a physics PhD. So if you don't and you want to work in it, then be prepared to learn fast and get used to being out of your depth all the time, which I quite enjoy. But once that's true, and the more you can learn before you make the jump, the better off you'll be. Quantum computing development is inherently multidisciplinary. Only the very small bit at the bottom is the actual quantum bit. It requires many skills across technical, organizational, business disciplines. So don't feel that you need a physics PhD to enter the industry. Even on the technical side, there's plenty of need for people with skills in materials science, microwave engineering, FPGA firmware development, software development, etc., etc. So the more quantum background you can give yourself, the better off you'll be. But don't be scared off if you don't have that already.
Open to curious minds, by the sounds of it, as an industry.
Perhaps that's a good way of saying it, yeah.
One final tricky question for you. How do you think quantum computing is going to change our world in a sentence or two?
I think if Bitcoin gets broken, we're going to hear about that. I think the things that are going to make more of a difference probably will never be seen by the general public. So accelerating drug development and pharmaceutical, we don't see that behind the scenes stuff. What we're going to see is things like when Bitcoin gets broken.
Nathan, it's been a brilliant conversation. I've really enjoyed learning about quantum from you. Thanks so much for joining us. It's been a real pleasure to hear your story and your insight and all about TreQ. Where do we find out more about TreQ? The website's trek.tech.
Absolutely. TreQ, every quantum computing has a Q in its name, treq.tech.
Brilliant. Well, we really look forward to seeing you guys more in our future. And thank you very much again.
It's been an absolute pleasure. Hope we can do this again sometime.
That wraps up this episode of Digital Humans Podcast. If you enjoyed the conversation, don't forget to subscribe on your favorite podcast platform so you never miss an episode. Thanks for listening, and we'll see you next time.